Shit, what's going on? Why can't I rescale this thing? Oh, because I log it. Okay. But why do I need to do this every time? Anyway. Okay. Streaming should be fine. Okay. Any question from last time? Well, a quick review of last time. We go very quickly through classical computation last time. Okay. So we got from Turing machine all the way to P versus NP. Okay. And yeah, so hopefully this gives you a quick review or quick introduction to classical computation theory if you haven't seen about it. And sorry, let me do this. Yeah. And yeah, the important question in classical computation is this Pn versus NP problem. And some interesting things. So as I've been thinking this a lot, but the most important thing here is we need to know the big O notation. Okay. And yeah, so there are really those 5 big O notation that kind of mean less or equal to, less to, greater equal to, greater to, or equal. And those relationship all are like up to a constant. So like if f is big O of g equal to big O of g, it means that f is less than some constant times g, and these are all talking about symptomatic. So there is going to be some scaling parameter, for example n here, and yeah, and we'll write this thing and think about what happens when n go to infinity. So this is kind of like calculus. It's similar to calculus where you calculate this limit of xa of f limit of f divided by g, but yeah, sometimes it's weird because it's a bit different because say here you might want to say f divided by g go to c in a limit, but sometimes they might not have a limit, so it's a little weird. But as we see, it is a very strong correlation to calculus, and from calculus we know basically those set of things. So y is less than basically polynomial to some log, and it's less than some polynomial to or I should say less than. Okay. Yeah. Yeah. So from calculus you kind of have this idea of what. So constant is much less than any polynomial and log of x, and much less than poly of x, and it's much less than exponential of x. Okay, and yeah, then sometimes we'll ask you find the big theta or some expression that you basically need to find the singular scale or the phases. So if there is the exponential, it's going to scale the exponential, and you have a polynomial, and you just look at the highest order, etc. Okay. And yeah, so that's classical computation, and the other very okay. And there is a circuit model, there is a Turing machine, and there is a reduction. Reduction is something that's very useful in all kinds of concepts. It gives us the concept of complete problem, and they actually also give us the concept of which problem is harder than which. And where is the reduction? It's a little lower, I think. Yeah, and it's kind of like when you do algorithm, you will run your algorithm and then you will cause out some algorithm. And although it's a sub-algorithm, in terms of theoretical computation, theoretical consideration, it actually means the sub-algorithm is solving a harder problem. Because solving this problem enable you to solve another problem. So this problem B is harder. So algorithm for problem A calling algorithm for solving problem B, and so this is the reduction. Yeah. Okay. Anyway, that's a quick review of classical computation, and here we can schedule. So jump really quickly to quantum computation, a different topic. So yeah, so finally we can start quantum computation. We've been talking about quantum mechanics and computation. So now we combine and talk about quantum computation. And yeah, so how we define quantum computation is similar to the circuit model definition of classical computation. Okay. So we also define quantum computation in circuit model. So you see this is very similar to quantum computation. We have wires and gates, and then we have something extra. We have a measurement because in quantum mechanics you need to do measurement. Okay. So yeah, parallel to classical computation, you have the wires and gates. So wires now carry quantum information. So each wire we think as a qubit. In classical, it was each wire was 1 bit. Now it's a qubit. Okay. So the Hilbert space for each wire is C squared, so 2-dimensional space. And then we might have n wires, and it's n qubit. And then, as we know, the total Hilbert space will be the tensor product of all those space. So it's a tensor product of the first wire, second wire, third wire, fourth wire. So it's a 2 to a 4-dimensional space here. Okay. And then we have gates. Okay. And now things are a bit different. So classical gates, you have some truth table, so you have input and output. But quantum wire can only need to obey quantum mechanics. So each gate is a unitary operator. Okay. And yeah, so it's a unitary operator that apply on some of the wires. Okay. And so if you think about the total unitary on the whole space, you're going to be U tensor I on all other space. Okay. And yeah, so each gate is a unitary operator. And then we have something we don't need to do in classical, that is the measurement. Okay. So we are manipulating quantum information inside those wires and the gates. And the end we get some quantum state here, but we want some classical outcome, then we need to do measurement. Okay. So the end will do some measurement, and sometimes you have different notation where you measurement in different bases, because like we say there are many different kinds of measurement, but also as we say actually everything is kind of equivalent to measurement in computational basis. Okay. So most of the time, we will just assume when we write measurement, we will just assume it's a measurement in computational basis, because that doesn't really change the computational power. Okay. Like for example, remember when we say you have a generalized measurement, then it can be done by projective measurement with some extra unitary and some NC loss. Okay. And yeah, so we think doing computational basis measurement doesn't change the power of your algorithm too much, and so we just constrain our measurement in computational basis most of the time. Sometimes you will measure in say different bases when that makes things look a little nicer, but those times we'll make a special notation on it. Okay. And so I guess we also will kind of skip here a little bit about input. Okay. So input. Okay. And so classically you can input any string, and so I guess it will be wrong here. So if you are solving some classical problem, you want to input some classical string, and so if you input a classical string, then you are basically going to input computational basis states like x1, x2, x3, x4. So like x1 equal to 1, then it's a 0, and x1 equal to 0, then it's a 0 state, and x1 equal to 1, then it's a 1 state here, etc. Okay. And but sometimes you will also just a lot of the time you will just input all 0 state here, for reasons you will see later. Okay. So I guess I don't want to say this. yeah. So if you are thinking about you have an input string here, then it might be like kx1, kx2, kx3, kx4 here. Okay, and anyway, and but yeah, really the input will change depends on what you would want to do with your quantum circuit. Sometimes you will even like input the unknown quantum state, etc. Okay. Yeah, but actually, a lot of time you will just input the standard basis of your state into your circuit. Okay, and and we'll see why that's a reason later. And I guess we didn't say here and something extra. And remember in just last time we say in the classical circuit model there is the problem of uniformity. So we're saying like if you don't want your answer to get hard coded, you want your circuit to be generated by a Turing machine. So here you have a similar issue. So if you want your circuit, so you want your quantum circuit to be uniform, because then it means like the circuit description is generated by actually also a classical Turing machine, because it's a bit weird to define quantum Turing machine. Okay. So generated by a Turing machine. Okay, so that's uniformity. Anyway, so that's the definition of quantum circuit. And any question for now? No. Okay. And yeah, so you see it's really similar to classical circuit model, but there are some differences. So the first thing is something we already said, that is there is no fan out. And that's because of no cloning series. So you cannot have one wire that's split into two wires. Okay. And yeah, so you can have side split into side. That's something you can do classical circuit, but it's not possible in quantum circuit. And actually, so this conservation of a number of lines is very strong here. So actually also every gate is reversible. Okay, so that means the input number of input wire is equal to the same number of output wire, and yeah, and then you can always reverse what you do on some gate, because every gate is unitary, and unitary is a reversal matrix there exists. So you apply some unitary, then you can apply the dagger of unitary, and the dagger of unitary is just a U inverse. So yeah, U dagger U equal to identity. So if you apply U, then apply U dagger, then equal to you apply nothing. Okay. And also something we forgot to say here. So just like a classical circuit, time flow this way. Okay, time. And yeah, so here it may look a little confusing. So this you have a U dagger here, and it kind of like a U dagger U here, but this actually is same as this, because the time flows from left to right when we write the circuit, but when we multiply this on some state side. Okay, I can use green. Can you probably use green here? Okay. Yeah, but when we multiply this on some state side, then we actually resolving this right to left. So there is some of this reverse ordering. I think it's a little confusing, but it's just a notation thing. And be careful, don't confuse yourself. Okay. And yeah, so the number of wires that I really conserve. And as compared to classical you really don't have this thing. Right? So classical, remember we have the AND gate. So like classical, you have like AND gate. I forgot how to draw. I think it's drawn like this. Classical, you have AND gate, and you will have 2 line in and 1 line out. But this is not reversible. So this is not quantum. This is not possible in quantum, yeah, because it is irreversible. Okay. Okay. And so what are the gates that we can do in quantum? Well, basically any method you can do, but we like to piece together our quantum circuit in some of the basic gates, just like classical, you favor the and or not to piece together your circuit. And quantum, we also like some basic gate, and we have seen most of them already. So first of them is this Hadamard gate. Okay, and remember it's a gate basically changing, switching the x basis and the z basis. So Hadamard apply on the 0 state or 1 state will become plus state and minus state, and apply on plus minus it becomes 0 1, and it has this matrix. And then we have our favorite polys. Hopefully through all the homework you are already very familiar with it. So once again, poly x is 0 1 1 0. Poly y is 0 minus I 0. Poly z is 1 0 0 minus 1. Here, so in the gate notation, we recognize this. So Hadamard, so the gate all written as a block, and Hadamard you just write a big H inside. Then poly x y z you just write big X, big Y, big Z inside. Okay. And then to get a universal quantum circuit, you need more gates of those. Okay. So we have two extra gates that people usually do, and they are really related to poly Z. So first one is the phase gate, and there are two different conventions. People either call it P for phase and S for some other non-conventional convention. And so this is 1 0 0 I gate, and you can see that this is a square root of the poly Z gate, because 1 square root is 1 and minus 1 square root is I. Yeah. And then there is another gate that's a T gate. So it's also called pi over gate because it later we'll see it means that pi over 8 rotation in Z basis, but in Z axis. But anyway, so that's the square root of this S gate once again. So it is 1 0 0 and e to the I pi over 4. So I is e to the I pi over 2. Okay. So yeah, so here are the notation x, y, z, s, and t. Okay, so those are the 1 cubic gate that people use a lot. And for some reason, actually, people, I guess, yeah, for some reason, T gate is actually more popular than S gate. But we won't talk about that probably in the course. But anyway, so 1 cubic gate, and then we have 2 cubic gate. So 2 cubic gate, first is the C naught. We already seen it. We already seen it when we talk about, I think when we talk about teleportation. Okay? And in circuit model, then it's written this way. So wire, and so 2 cubic gate, so you have 2 wire here. And it's not symmetric between the 2 wires, so it has a control qubit and a target qubit. So it's written in this way, so you have this solid dot here on the control qubit, and you connect to your target qubit, and you draw this circle plus. Okay, so this is CNOT gate, and as we know, it has this matrix. So the matrix can be viewed this way, and or block way. So it's like when the control qubit is 0, it does nothing, and the control qubit is 1, you apply X on the target qubit. And so you can return that. So you can return what the CNOT gate do on the computational basis as this. So assume AB are computational basis, so A is 0, 1 and B is 0, 1. Then you apply CNOT, what happens? So the control naught, you will do nothing to the control qubit. So whatever is 0, 1 here, you go to 0, 1. And then as we said, if A is 0, then it doesn't do anything to the B qubit, so B is still B. But if A is 1, then you apply a NOT gate on B, so B becomes the negation of B, and it's basically 1 minus B. And another nice way to write this is B circle plus 1. So yeah, so this circle plus is is XOR, and so this basically means plus mod 2. Okay. So B plus 1 mod 2, and obviously that would be a negation of B. Okay. And yeah, so we will stick with this plus notation mostly because it's easy to do computation. So because it basically just do plus and then you just do the addition and mod 2. Okay. And yeah, so we have this nice formula. You see that when you can combine all those things together as C naught on AB equal to A and B and O plus A. Okay, because when A equal to 0, then nothing happens, and A equal to 1, then it's B plus 1. So it's A and B plus A. And so this is what C naught do on computational basis. And so by this actually already specify the whole C naught, right? Because on computational basis, so basically you are specifying every column here. And yeah. And we'll see that this is actually a good way to do to compute what your circuit do. Also, you just know how your gate act on every computational basis element, and you expand what your circuit do on computational basis. And anyway, yeah, we have a nice algebraic expression for C naught here. And yeah, as we say, it's only on computational basis, but you have other state, then you just write things as a linear combination of computational basis and use the linearity of your gate. And for example, you can think a little bit about what C naught do on the plus 0 state, which is, okay, so let me help you a little here, which is 0, 0 plus 1, 0 state with 1 over square root 2. Okay. And yeah, so that's C naught, very important. And then we have a bit of generalization of C naught. So this control unitary, and yeah, so you see they are very similar to C naught. Is identity when the control qubit do not is 0, and you apply a unitary on second qubit when your control qubit is 1. And it's written this way. So you have this solid dot and a straight line as a control, and then you just write whatever unitary you want to apply here in this block. So the control unitary, and you return in the matrix form is I and U. And yeah, so what I do is see you on a tensor state, so some computational basis A and some whatever state phi, and it will be A and oh, here we have a typo, A and U to the A phi. So if A is 0, then U to the 0 is identity, and A is 1, U to the 1 is U. Okay. Yeah. And then okay, so we generalize C naught to control whatever unitary, then we kind of go back a little bit and get a special kind of control unitary, that's control Z. Okay. So yeah, so the CZ gate. So I write it as CZ here, but sometimes people just write CZ. Okay. But anyway, so CZ gate is special because it's also used a lot, and it has a special notation like this. So it's a bit funny to like a two control. Okay. So so yeah. So this solid dot, straight line, solid dot thing is control Z gate. Okay. And so you're seeing this is funny because then how do I know which one is the control gate, control qubit? Because this is the notation for this qubit being a control. And the interesting thing is we can write it this way because control Z is actually symmetric between the target qubit and the control qubit. And you can easily see this if you write down its matrix. So it's 1, 1 and 1 minus 1, right? So as this form, so the first block is 1, 1 and the second block is 1 minus 1. And by thinking about how you apply on computational basis, right? So these so this is like 0, 0, 0, 1, 1, 0, and then 1, 1. So you see that you apply a -1 phase only on the 1, 1, only on the 1, 1 input. 1, 1 input is symmetry between the first qubit and the second qubit. And yeah, so this gate is really symmetry between the first qubit and second qubit. So you can write it in this interesting form. Okay. So that's a control gate. And then we have the swap gate. And swap gate, as the name suggests, is swap the first qubit and second qubit. So swap gate apply so whatever tensor state, so some state psi, tensor some state phi, will get some state phi and some state psi as output. Okay. So maybe draw it here a bit carefully, so you have psi, phi, and you apply swap gate, you will become phi psi. And if you write down the matrix, you will have this. And so basically, well, you want to swap, also do swap on computational basis, right? So 0, 0 should go back to 0, 0, 1, 1 should go to 1, 1, and the 0, 1 should swap between 0, 1 should swap to 1, 0. Okay. Okay. Any questions so far? I think today we'll finish the gates. Okay, so 1 qubit gate, 2 qubit gate, then we also have multiple qubit gate. And I think multiple qubit gate, there's only one that's famous, that's this Toffoli gate. And it's basically control not. So it reads like this. So it's really like C not, but there are two control. Okay. And so there are two controls, so if you apply this computational basis state, those are control qubits, so it won't affect the input state. So A in still A out, B in still B out. And on C, then you apply a NOT gate. So it's double control, means that only if both of them are 1, then you will apply the control on the thing on the third qubit. Okay. So you apply this NOT, so basically +1 only where A and B both equal to 1. And you can express AB both equal to 1 as this A times B, because A times B is 1 only if AB both equal to 1, because they are boundary 0, then A times B is 0. Okay, so you can also reason this algebraically. Output is AB and C O plus AB. Okay, and yeah. So why do the people like Toffoli gate is a bit funny? It's actually because from classical computational theory, so you can prove that this Toffoli gate or CC NOT is universal for classical computation. So just like the NAND gate, if you only have the Toffoli gate, then you can do every classical computation. And but also reversible, as we see here, is a quantum gate. Okay. Yeah. And so it's a nice way to kind of bridge classical computation and the quantum computation. So for example, this proves that quantum computation is universal for classical computation. Because remember we had this here. Remember we had this constraint that every quantum gate needs to be reversible. And so we cannot have AND gate as a quantum gate, so it's a bit fishy whether quantum computation can even do all the classical computation. But here we show that it's possible, because Toffoli gate is a valid quantum gate, and so quantum computation is universal for classical computation too. So, or otherwise they say quantum computer are universal for classical computation too, because you can piece things together with Toffoli gate. Okay. Yeah. And okay, then a little notation thing. That is this. So remember when we say control, we always write this solid dot, and there is also empty dot. Okay. So sometimes people write this empty dot, and then it means control on 0. means you apply this u only when the first qubit is 0, instead of the solida, which means the first qubit is 1. And so this is equivalent to the solida thing, but you apply NOT gate before and after. So swap then 0 and 1, then you apply your control, then you swap 0, 1 back. And yeah, so this is just a notation. Okay. So we have a lot of definition, and let's see some example of actual calculation. Yeah. And yeah, some of those are from chapter 1, some of those are from chapter 4. But anyway, so first thing is swap gate. And swap gate, you can actually do it from having 3 C0 gate. Okay. And so you apply C0, first C0 this way, second C0 this way, and third C0 this way, and we will say that this is a swap gate. And yeah, and so we show this on computational basis only. And I think in homework you are asked to show that if swap gate is doing this AB to BA on computational basis, and then you will actually do what we say on general quantum state. It's not too hard. So we want to swap psi-phi for general quantum state. Here we also only show on computational basis. Anyway, so we show what the circuit do on computational basis state. So you have an input here AB, and we see that what happened to after each of the C0. And this is where the algebraic expression is very useful. So we can have AB input, then we can just do this algebraic computation. So AB, and as we say, the C0 will add the target to add the control to the target. So AB become A plus B, AO plus B, and this will all means addition mod 2. Okay? And then A plus B, and then we apply this. So here we have A and A plus B, and then we swap the control and target. So then now we need to add the second qubit back to the first qubit. So second qubit to first, so second qubit stay A plus B, and you add back to the first qubit, so A plus B. And then we do some algebra, right? So A plus B is like 2A plus B. But everything is mod 2, so 2A is 0. Okay. So this 2A plus B actually just equal to B. Okay. So yeah, this is an interesting trick we'll use a lot of time. That is when you do this O plus thing, then A plus A is equal to 0. And yeah, so you get B and A plus B here. And then you do a similar thing once again. And so then you add B to A plus B once again, and you have A plus B, and once again, that's B plus B equal to 0, so that's just BA. Okay. And so this is a general way to do computation to see what your circuit do. So as we say, you expand in computational basis. Well, here we are lucky because everything always stay in computational basis. It's quite classical. But in general, you can expand everything in computational basis and just do what your each gate do on computational basis. And yeah, and this will be, how should I say? And this will be a little easier than say you write everything in a big matrix. Okay? So it's very tempting to write. We have a matrix for everything, so it's very tempting to just expand everything out as a giant matrix and do a matrix multiply on vectors and to calculate what your circuit do. Okay, it's possible, but it's very how should I say? Very computational heavy, because you see the matrix is really big. So say the C0 matrix we have here, you need to write a whole bunch of 0 here. You need to write this 4x4 matrix whenever you apply a C0. There are 16 number here. So you see that if you want to do this C0 calculation here, so like for example the calculation we just do here, if you want to multiply all the matrix, then it's going to be like a 4-dimensional vector. then applying 3 4x4 matrix, and so there are a lot of handwriting you will do, and a lot of time you will make a mistake. So although it's also a legit way to do it, but I just won't say it's not recommended. This computational basis calculation, you can see it's much cleaner and less prone to error. Okay. And yeah, so that's example 1. Then example 2. And so this is kind of what we say we'll do. Okay. And so this is what you want to do, copying. Okay. So in classical computation, if you have whatever a here and a 0 here, then you do C naught, then you will get a here. Okay. But quantum computation, we see copying is not quite possible. So we have whatever side here and equal to a0 plus b1. And let's see what happens when you C naught it into 0 state. Okay. And yeah, so as we say in classical computation, it's copying. So if you have the 0 on the first qubit, it will become 0, 0, and 1 on the first qubit, it become 1, 1. Because, yeah, you add 1 to the 0 and become 1. And, but if you have a plus state, okay, so this is some quadrant as before, so we have a plus state here. And, so I guess we should actually see the calculation here, okay. So C naught A0 plus B1, and as we say, we expand into computational basis. So it's A00 plus B11, and then you just know what C naught do to the computational basis. So 0, 0, you add 0 to 0 is still 0, so it's still A00. And B11, you see 1 here, you do something, so you add 1 to 0, and it becomes B11. So yeah, so this A0 plus B1 times 0, it becomes A00 plus B11. And you see that this is an entangled state when A and B are not these 0, 1 cases. And also in particular, so as we say, this is not copying for general quantum state because we know cloning is not possible. So if you have input state is plus, so square root of 0 plus 1, and the output state will be the square root. So you have square root 2, and you have square root 2 square root 2. So square root 2 of 0 plus 1, 1, and you see this is a very entangled state. This is an EPR pair. So yeah, so this is how you create EPR pair. You have a 0, you have plus and a 0, and you apply the C naught, then you get an EPR pair. Yeah. And as we said, this is not a plus tensor plus state. Okay. Okay. Should be on schedule. I hope. Oh, we are a little slower, but I think it's okay. And yeah, so let's finish seeing all those circuits. Then another example. And so C naught and Z gate, and we see that C naught gate will commute with Z gate. So Z gate once again is 1, 0, 0, minus 1. And okay, so we didn't quite say, but it's easy to verify that Z on A equal to minus 1 to the A. Okay, so you get the minus 1 phase. I should, okay. Yeah. And so what Z do on computational basis. And yeah, so you can check it here quickly. So Z on 0 is still 0, you do nothing, and minus 1 to 0 is nothing. And Z on 1 is minus 1 and 1 kit. And yeah, so minus 1 to 1 is minus 1. Okay. So A, B, and okay. And so if you have this circuit, then your AB will become, so we are also once again looking at a different step of the circuit. Here, here, and here, here. Right. And so we see the AB, then you apply Z on the first qubit, so you get a minus 1 to the A on the first qubit. And then you do the C naught, so it's A plus B. And on the other hand, if you apply C naught first, you get A and A plus B. Then you apply Z on the first qubit, you still get minus 1A to the and the A plus B. Okay, so that's Z. And finally, then we see the EPR. So this is like an intentional example 2. Okay, so if we start with the standard basis 0, 0, how we get EPR pair? where we want to apply C naught on a plus state, and how we get a plus state is you apply hidden on a 0 state. And yeah, so what happens is you get plus state here. So let's see this once again. So 0, 0, and then you apply hidden on the first qubit, then it becomes plus tensor 0, which is 1 square root 2, 0, 0 plus 1, 0. And yeah, then the same calculation. So so C naught will add the first qubit to the second qubit. So 0, 0 stay 0, 0, 1, 1, 0 become 1, 1, 1. And that's the EPR pair. And actually, this circuit is a little more general than creating EPR. This is actually a swap between. So this is actually a change basis between standard basis and the standard basis and the Bell basis. Okay. So this is how you change it between and forth standard basis and the Bell basis. Just this Hedema and C naught. Okay. And do we have time? Yeah, we should have. And I think the last two example. Oh, we also have a tip. But anyway, so we're a little slower. Okay, so let's see this very quickly. So we can also write what we do on super dense coding and teleportation in terms of a circuit. Okay, and yeah, so maybe a quick reminder. So what this super dense coding do is Alice get beta 00, and it will then depend on what string Alice is going to send. He will apply X or X and Z on her part. Okay. So remember the super dense coding, and so we are writing both Alice and the Bob part on this circuit. It's a bit funny because you don't see a separation. But basically, the first qubit is Alice and the second qubit is Bob. Okay. A here and a B here. And so Alice will apply X and Z depending on what is on her qubit. And here we have the example where AB is 1, 0. Okay. And as we said, then after Alice applies AB, then this whole state is in one over 4 Bell state. Okay. And then at some point, Alice will send her qubit to Bob. But in circuit model, we cannot really see this. But anyway, at this point, Bob holds both copy, and it's in 1 over 4 Bell basis state, depending on what Alice do on this AB here. And as we said, this circuit is a translation between Bell basis and the standard basis. So you do the reverse of it, you will change from Bell basis back to a standard basis, then you do standard basis measurement. Okay. And similarly, you do teleportation. And here we have a little more better, I guess similar. Okay, so here teleportation, we start with Alice holding 2 qubit and Bob holding 1 qubit, and 1 qubit is what Alice wants to teleport, and the other qubit start with maximum starting the EPR pair, and then Alice do Bell basis measurement on her part. And then we should get 2 classical outcome, and should send a classical outcome to Bob, and Bob can do correction. But we are a little short on time, so I guess we'll leave the example here. You can check it once again. Well, it's similar to what we had before, but yeah, you can check it once again that everything is correct. Okay, and yeah. So I want to skip a little bit and let's go back to this tip. Okay. So as we said, this is a general procedure of how we work, and we want to write a state H time step in computational basis, and then we want to apply the gate corresponding to each register using this logical expression. So we want to basically write this. Well, we want to see what each computational basis they become, and we have some. Nice shorthand here, so we know Z on whatever state is going to be -1 to A and A, and C naught AB, as we know, will be A and B plus A, so it will add A to the control qubit to the target qubit. And okay, I guess the notation is a little the C notation is actually a little confused, a little ambiguous, because we didn't really say which is target, which is control. So, but in a circuit, it's clear because we have the control and the target. But anyway, C not, then we have the ambiguous notation, but just keep it like that. I think it's not too much trouble through the course. And anyway, so back to the logical expression, and yeah, so the most thing we do is z c naught hegemon, and I guess we should also have x here, right? So xa equal to a plus 1. Okay. And yeah, then hegemon will swap between 0 and 1, as we know. And so on combination basis, hegemon 0 will become plus, and this is about, I would say, is 1 over square root to 0 plus 1. And minus is 1 over square root to 0 minus 1. So this is an annoying thing that will give you more computational basis state as outcome. You can see all other things just map one computational basis state to one computational basis state, so they are nice. Okay. And yeah, as we say, you can write everything out also as a 2n dimensional vector and aggregate as a 2n by 2n matrix, 2n by 2n matrix, but it's very computational heavy. Okay. And you can feel that instead of having this A, B to A and B plus A computation, you need to write a 4x4 matrix for C naught, and it's a lot of handwriting. Okay. And okay, so this is where we want to say, okay, I actually have 3 minutes, so let's go back to see the tape. Okay, is anyone question yet? Now let's try to go through this teleportation once again. Okay. So teleportation, you have psi as a plus b, a0 plus b. And here we'll do something that actually we like to do a lot, that is we omit the normalization. And that's because whenever you do hegemon, you get a lot of 1 over square root 2. But it's actually a little annoying to keep track of that, and at the end you can usually just guess what you know. You can just put back your normalization. So here we are being lazy, we throw away all the 1 over square root 2. And and anyway, we start with a0 plus b. And so at the start we have a0 plus b tensor 0, 0 plus 1, 1. And so that's a0, 0, and well, then just expand out a0, 0, a0, 1, 1, and b1, 0, 0, and b1, 1, 1. Okay. And then you do c naught on the first 2 qubits, so you add the first qubit, the second qubit, and so first qubit 0, nothing happens, and first qubit 1, they become 1, 1, 0, and first qubit 1, and so this 1 becomes 0. Okay. And then you do hegemon, so now you get more state as outcome. Okay. So the first state becomes, so 0 become plus and 1 become minus, and you expand it out, and that's well, you are going to have a state here. So it's going to be 0, 0, 0 and 1, 0, 0, etc. And so we skip the middle step, and so it's going to have, but we just do counting, so it's going to have a state out, and then we group together what the first 2 qubits is in the standard basis. So there's a 0, 0 part, that is a0 plus b1, and the 0, 1 part is this a1 plus b0, etc. And so you see, when you do computational basis measurement, you will pick out 1 over the 4 here. You do computational basis measurement, you pick out 1 over the 4 here, and you will collect the third qubit into the corresponding 1 over the 4, and yeah, and then it's the same analysis with interpretation, where we say, well, those 4 things can be corrected by the x and z operations. You can check it yourself once again. Okay, just on time. And so nice, this is exactly as planned schedule. So this is where we will, okay, so let's change the color. So this is where the scope of midterm will be. Okay. So midterm, we'll we'll have question until this part. Oh, sorry, maybe not this page, maybe next page. Okay. So yeah, so today's scope is where we'll have midterm, and the midterm will be next Thursday. So this is midterm. And but also because next week is midterm, so this week we will have no homework. But yeah, we will probably have some homework question. So those kind of calculation will hand out some question along with answer, so you can prepare for midterm. Okay. So yeah. Sorry for a bit overtime. Any question? Otherwise, let's see you on Thursday. I think Thursday we'll keep ahead of schedule. We'll talk something that's not the midterm, but well, going to be a nice theoretical foundation. Okay. Okay. So yeah, see you on Thursday.